Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at some classroom strategies for your calculus end-of-course exams. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight we're really lucky to be joined by our two panelists, Fan Disher and Vicki Carter. Fan has taught all mathematics courses ranging from 7th grade through college algebra in her 43 years of teaching, most recently teaching pre-calculus and AB and BC for the last 28 years. She's also an AP Calculus reader, wrote a Louisiana state curriculum for Algebra 2, and presents numerous workshops on middle through high school teachers about mathematics and graphing technology. She shares many of her calculus and pre-calculus classroom activities at state and national conferences and in her store, Fan's Math, on Teacher Pay Teacher website, on the Teacher Pay Teacher website. Fan, thanks so much for joining us tonight.
I'm excited to be here. Always glad to talk about math.
And Vicki has been teaching high school math for 42 years and currently serves as the math department chair at West Florence High School. She's the former co-chair of the AP Calculus Development Committee and served as an exam leader at the AP Calculus reading in the summer of 2018. She received the T-Cube Leadership Award in 2015, and Vicki has served on TI-Nspire authoring teams and has presented at many national, state, and local conferences. So, Vicki, we're excited to have you with us tonight.
Thank you, Mike. It's a pleasure for me to be here tonight and talk with everyone about calculus.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Vicki or Fan using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the top of the WebEx menu and choose Audio Broadcast. At this point, Fan is going to discuss our agenda.
We're excited to be with you and try to go through some of the things you've already done in the first semester. We can't cover everything, but most of you have finished limits and derivatives. So we've looked for problems that don't get addressed in the second semester and hopefully don't get forgotten. So I'll be looking at several types of limit theory problems, and then I'll turn it over to Vicki, and she'll do some graphical analysis review and particle motion. And then Vicki will show you a few of the calculator skills on the TI-Nspire. She'll give it back to me, and I'll show you the skills on the TI-84 Plus.
Thanks so much, Fan. And Vicki is going to discuss our expected outcomes.
Okay, tonight, as Fan discusses limits, we hope to review a little bit about asymptotes and the limit definition of the derivative, and we'll also talk a little bit about L'Hopital's rule. When I'm talking about analysis of functions, we're going to primarily look at what the graph of a derivative or what we know about a derivative will tell us about a function. So we're going to sort of analyze f prime, and f double prime. We'll do a little bit of exploration with particle motion, both the AB level, which is motion on a line, and BC level, which is primarily dealing with parametric equations and motion in a curve. And then, as Fan said, we're going to wrap it up with some calculator skills on both of the two types of calculators, the TI-Nspire and the TI-84.
Vicki, thanks so much. Fan, you have control. Feel free to share your screen.
All righty. Let's see. We're going to share screen here. My screen. Got it?
Yes.
That looks good, Fan.
Sounds good. All right. So here we are. I'm going to start off with you with the three different topics, as Vicki said, that we want to make sure that you keep reviewing with your students during the second semester. They don't tend to come out when we're talking about integral calculus. One of them being asymptotes. You know, we look at curve sketching in the first semester, but then we don't, when we do the integral calculus, we don't. Another, that limit definition of derivatives has been showing up more and more on the AP test, so we want to make sure that they keep that in their brain. And the last one, we're going to hit L'Hopital's rule very lightly because there is a whole webinar on L'Hopital's rule, but not teaching L'Hopital's rule, but more in the fact of reviewing L'Hopital's rule. So I'm going to start off with asymptotes. Just a little content, you know, vertical asymptotes, the limit as x approaches that vertical asymptote, the y's approach infinity. I really don't like saying the limit is infinity. I tell my students to say y is unbounded. It doesn't exist, but the y's do approach infinity. If it's a horizontal asymptote, we know as x approaches infinity, the y's approach the horizontal asymptote. And just to give you an example, here's a picture of a vertical asymptote and a horizontal asymptote. The limit theory would be that as x approaches 2, the y is approaching infinity, and as x approaches infinity, the y approaches 0. The students forget that we need to approach both a positive and a negative infinity to find those asymptotes. So just to give you a few examples of problems that are on some of our practice problems that have been out there. This one I kind of made up. Look at what is being asked. Notice it says there are two asymptotes, x equal 3 and y equal 1. Now, do your students confuse which one's vertical and horizontal? I know mine do. So we're hoping they will realize that this one is your vertical and this one is your horizontal. So the concepts, remember, x approaching the vertical, y is going to infinity, x approaching infinity, y is going to the horizontal. So that's the big picture concept. So we want the students to look at this, okay, start eliminating. I see x approaching infinity, so I'm down, not too good with this mouse here. There, to C or D, all I have to do is look at which one's going to be. So there we go, 3. Now we know that this is a non-calculator problem, but we know that the calculator can reinforce what we're talking about. So here's a particular example. It's positive. We have a vertical at x equals 3 and a y, and a horizontal at y equals 1. We put it on the calculator, we see a nice graph. Now, when I do a calculator approaching infinity, I make my windows, the x is a whole lot bigger, so it's really going to infinity. And I also put the grid on so that they can tell that this particular problem is closing in on a particular horizontal asymptote. This is a really good problem because it approaches that horizontal asymptote between the top and the bottom. And you can see even in a list how my steps going up by 20 so that I get them closer to infinity, and therefore it looks like it's closing in on that horizontal asymptote. Now, this is the TI-84 pictures. All I've put here is just pictures that are on the TI-Nspire. All of these slides are on a handout on the TI website, and I just wanted to make sure that if you're more comfortable with the Nspire, you can refer to this particular page. Here's another practice problem. I mean, it doesn't even look like calculus, it looks like pre-calculus. And therefore, we're asking them for one vertical and one horizontal. I'm going to give you a minute just to see what it looks like. Now, definitely, I don't see a vertical in A. I see a vertical in B, but, you know, they forget that there really are two verticals in B. E, they forget about what the E does and that E approaches things differently when it goes in different directions. And they look at this one and they don't see a minus, so they must not have a vertical asymptote at all. Just to give you a picture of all the graphs, here's A, no vertical, one horizontal. Here's B, 2 vertical. Here's C, 2 different horizontals. And here is D, because they forget you can really factor two perfect cubes, two perfect cubes, and they'll say, what, 4 is not a perfect cube? I know, I've heard it all. Here's the limit theory that goes with C. E, as x approaches infinity, this limit is 0, and as x approaches a negative infinity, the limit's -2. So there's 2 horizontals. So that says that your answer is D. Again, this screen is just showing you graphs that are on the TI-Nspire if you're more comfortable there. This is another interesting one that has actually 2 horizontal asymptotes. And the part that catches the students is the fact that the square root of x squared is really absolute value of x. And that plays a part when you are taking limits to both the positive infinity and the negative infinity. So the graph actually looks like this, going toward 2 different limits. Now, I've put the limit theory on here for you. Yeah, I know. Isn't it beautiful? But I'm not going to go through it. You can pull up the handout and look at it. The key is when you divide by the highest power of x, which we know that's the concept, is that this 1 over square root of x squared is positive in this case, and this 1 over the square root of x squared is negative, or the opposite of, because you're approaching a negative infinity. That's how you end up with 2 different asymptotes. It's a very beautiful problem. I just want to mention 2 more places that have 2 horizontal asymptotes. That's kind of the new concept that my students encounter in calculus. In pre-calculus, we have mostly 1 horizontal asymptote. In calculus, they are exposed to 2 horizontal asymptotes. Logistical growth, which is actually a BC topic, but it has that old E again, and that E can give us 2 different horizontal asymptotes. And then the only inverse trig function that seems to keep popping up is arctangent, and again, it's got 2 horizontal asymptotes. So keep in mind the limit theory: x approaching a vertical asymptote, y approaches infinity; x approaching infinity, y approaches a horizontal asymptote. Now we want to look at the second place that they kind of forget about, the limit definition of derivatives. I mean, we go through this whole process when we first start with derivatives, and then we give them the fast way to do them. And they forget that a derivative is actually a limit of the slopes of the secants. And we have 2 definitions that tend to pop up on the test, with the delta definition, and then this one where the second one where you actually find the derivative at a particular point. You don't find the numerical algebraic derivative. So here we go. This is a problem that was actually on the 2012 publicly released AP exam. And if they know this, then they look at this and say, oh, this is not a limit problem at all. This is actually just a derivative problem. So when I'm asking my students to work it, I go step by step. I say, oh, okay, what was the function? What was the value? Now take that derivative. And so the value would be 1/4. So your answer comes out to be the limit is 1/4. Now this is interesting because this particular problem was on one of the Facebook calculus pages just like this week sometime, last week. And a lot of people have said, well, you know, we can work this now by L'Hopital's rule. However, how many of your students would take the derivative of the log of 4 and get 1/4? Yeah, mine too. So if they recognize this definition of derivative, maybe it'll just make it faster and they won't do L'Hopital's rule. Well, sometimes this is really good. I know you've already taught it, but it's good to show them that the limit definition really is the derivative. I mean, here's the graph of this limit. That is not too hot, but you can trace close to 0. Notice I just went close to 0. If you went to 0, of course, y is going to be undefined, but close to 0, it's close to 0.25. And you can see it in a table even better. If you go up by very small increments, it's getting close to 0.25. So that's that limit. Now, what if we say, all right, this is log of x. So if we take the log of x, I can take the derivative of log of x at x equals 4, and this is the answer I get on the TI-84. They're going to freak out about this little part. Remember that the calculator can't take limits. And most of the time, the calculator is doing a derivative with the symmetric difference quotient and sometimes just can't close in close enough. So it actually is 0.25 because we just showed it analytically on the page before that. On a TI-84, you can also take the derivative from the home screen, and notice the derivative is 0.25 here, probably because it's been rounded off. I'll show you all of these skills at the end. You got all the screens here, but we'll go through some of these skills, such as taking the derivative at a point from your home screen and from your graph screen, when Vicki and I come back with the actual calculator itself. This is the same problem, TI-Nspire, if you're more comfortable with that actual calculator. This one I'm not going to go through. I just put it on your handout so that you'd have another one to practice with for your students. Same step-by-step stuff, identify the function and the value, take the derivative, and plug in the value. Now this is, but, you say, okay, I can work all of those problems by L'Hopital's rule, but you can't do it on this one. So you really do need to know that limit definition of derivative. And I have to tell you, this one came from the 2014 curriculum frameworks. I have to tell you, I missed this one the first time I looked at it. I said, hey, I know this. This is the definition of derivative. That's the derivative from the left is 2, the slope's 2. Now the derivative from the right is 2, the slope is 2. And therefore, the derivative is 2. I missed it. And then I looked up the answers. And the answer is just number 2. And then I said, okay, what's the problem? Well, the problem is that f of 3 doesn't even exist if you're coming from the left-hand side. You see this f of 3 right here? That doesn't even exist, so you can't be playing with that in the limit. I think that's the problem, definitely. So you can come in on the right-hand side, but if you look at the graph, this is a piecewise function. It's not continuous, which you would know if you plugged in 3 in both of them and took the limits. But you know derivatives don't exist at endpoints, but I can have a derivative, a left-hand derivative and a right-hand derivative. So what I'm showing you with this particular example is this isn't an analytic problem. It's a matter of knowing that this is the definition of derivative and what's going on. I think that was kind of tricky, though. This is the same problem and what a piecewise function looks like on your TI-Nspire. All of these are on your handout. Make sure you download them. Now, remember we have that second definition of derivative. So this is the second definition of derivative, where you're taking the derivative and finding it at a particular point instead of finding the symbolic definition and plugging in. Again, you could say, you could do L'Hopital's rule from it, but all right, what's the derivative of pi to the 10? Do you know how many true-false problems I've given on a test that and I will take 10 pi to the 9th, and it's false, but they'll tell me true. So you got to be careful, especially when you throw in something other than x, that's a constant, that they're not going to do L'Hopital's rule right. If they do that, 10 pi to the 9th, their answer is going to be 0. And guess what? It's one of the multiple choices. So you want to make sure that they recognize this as identify your function, the values at pi, take the derivative, plug it in. That makes your answer to be D. So those are the 2 types of definitions of derivative that you want to continue to review, and a lot of you give old multiple choice tests throughout the year so that they can practice on those particular type of problems. The third thing, and I can't leave without mentioning L'Hopital's rule, even though there is a webinar just on L'Hopital's rule, just because we have to constantly make sure that they remember that there are some conditions that have to be met before you do L'Hopital's rule. And there are 2 of them. One of them is that the 2 functions have to be differentiable. And the second condition is that the limit individually, be careful, don't say 0, 0. Each function has to approach 0, or each function has to approach infinity. Now, again, there's another form of the L'Hopital's rule that this isn't just C, but infinity. But you know that. So, for example, this one was actually out of the 2017 curriculum frameworks. And even though it's a multiple choice question, I like my students to do the justification first. Tell me the numerator and denominator functions are differentiable. Tell me that the limit of the numerator is 0, the limit of the denominator is 0. Once they have satisfied the conditions, now we can apply L'Hopital's rule. Now, again, this is kind of an odd one. Students don't know what we're talking about. Why is this true? Now, some of you prove it, some of you don't, but why in the heck is it true? So if you look at a table, you can show, put in both equations, the original one and the one where you took the derivatives right here, and look at both tables together. They both approach the same limit. So they have the same limit, the limit being 2. This is what the problem looks like and the table looks like on your TI-Nspire. So I hope that was helpful. I hope you got some idea of 3 limit situations that you need to keep constantly reviewing in your integral calculus. I know you do some limits when you get to integrals because of the integral definition, the definite integral definition. And those of you that do late transcendentals, you hit a lot of these topics again when you're pulling in logs and E and arc inverse trig functions. But if you do early transcendentals, you may want to continually add a few of these problems to your test at the end. All right, I'm going to pass it on to Vicki, and she's going to cover graphical analysis and particle motion. All right, let's see. I'm going to stop sharing. All right, Vicki, you ought to have it.
Okay. All right. So I have here a handout that I actually give my students. We do interactive notebooks in my classroom, so this is sort of a page that actually has a major tab on it that students refer to frequently. I adapted this from Lynn McMullen. He has a fantastic website about teaching calculus, and it's there at the bottom of the screen. So I basically like to think about graphical analysis. A lot of the questions deal with you have some information about the derivative. You might have the graph of the derivative. You might have the derivative function, and you might have a calculator available, and you want to graph the derivative. But it's the features of the derivative that tell us what we would know about the function. And so my students really like to refer to this chart. I actually have an anchor chart in my classroom on a big piece of post-it poster paper, and the students are constantly looking at it. Of course, I do have to take it down when we have testing situations, but I think it really helps them a lot. So let's look at an example of a question that would refer to this information, and this is also a release question. We have a derivative function that is rather interesting. It's the exponential e to the sine of x minus cosine x minus 1. We want to work on the interval from 0 to 9, and we want to know the intervals on which f is decreasing. So if we think about that chart that I had just presented, we would know that the function is decreasing when the derivative is negative. This is intended to be a graphing calculator question. We would hope that the students would graph this function rather than trying to work on their home screen with the calculator application. So what I did, first of all, is I have some TI-84 screens. So the first screen shows the first x-intercept of the derivative, and then we have the second x-intercept of the derivative, and the third x-intercept of the derivative. And we're going to need all 3 of those because if we're looking for where the function f is decreasing, we need to know when f prime is less than 0. So I have to clue my kids in and say, okay, yes, that's where the graph is below this x-axis for this function that we're looking at. And we see that little small interval from 0 to the first x-intercept, and then we'll have the next interval that is between those two x-intercepts. The beauty of the TI-Nspire is that we can show all of those at once, and so it's real easy to find the proper interval. And so if we look at our possible solutions here, we know we want to be on the interval from 0 to 0.633, and then from 4.11, in this case it would round to 4.115 to 6.916. And so that would be the correct answer. So let's look at a second question. And this one is a derivative that is presented. I think you're going to notice when you look at some of these calculator active questions on the exam, the students have to be very careful how they input their functions, and in this case it's the derivative. But again, I really want my students to think about this one graphically. So if we graph the derivative and we want to find a local maximum for the function f, and we just want to locate the x-coordinate, then what I need to think about on that chart is where does my derivative change from positive to negative. And so if we look at the graph, and in this case I just have the TI-Nspire screen because it would not be that different on the TI-84, then what I really want to do is find that second x-intercept, because this is where the derivative changes from positive to negative. And so once I have calculated that, then I would have my answer to the multiple choice question. So let's look a second at a little bit with parametric motion, and in particular we're talking first of all about motion along a line. So I, again, have an anchor chart with this information in my classroom. They also have some pages in their notebook about this, and this is just a reminder of some of the things that they need to make sure they know, and that's from first semester working with derivatives about particle motion. Sometimes in textbooks this is covered lightly, and so you would have to supplement possibly some motion along the line questions. So this is a calculator active again question, and it says we have a particle moving along an x-axis with a given velocity. So what we can think is that that velocity is really like our first derivative. And so the question is, how many times does the particle change direction as t increases from -3 to +3? So we just really would like to graph that function from -3 to +3. One of the mistakes that most students make is that they need to graph a function. They're t's, obviously, in a particle motion question because we're talking about t representing time, but they cannot use t on their calculator when they graph it. So I've had many students say, I get a slider when I'm working with the TI-Nspire, and I go, well, you're trying to graph with respect to using t as your independent variable, and you need to use x. So this is the graph we would want to look at. Notice that the students need to be careful. We have one time close to -2 that the particle would change direction because the velocity is changing from positive to negative. At this 0, or it appears to be a 0, we are not changing direction. And then at this 0 that's a little greater than 1, we are changing direction again because the derivative changes from negative to positive. So in this case, it would be 2 times that the particle changes direction. So I didn't pick a lot of questions about parametric motion because I knew that the majority of our listeners might be AB teachers and not BC teachers. But one of the things that I've noticed students tend to forget very quickly is if they remember motion along a line, that speed is the absolute value of velocity, they totally lose the concept of speed with parametric equations. And so we have to constantly remind them that there's a special formula for speed when they're working parametrically, the square root of the dx dt squared plus the dy dt squared. And so this is a fairly interesting question. The position of an object moving along a curve in the xy plane is given by 2 parametric equations, x of t and y of t, but we happen to know dx dt and dy dt. We don't ask them for the speed. Instead, we ask for the time at which the speed is 10 units per second. Now, I solved this on my TI-Nspire, but we could solve it on the 84 also. And in this case, I just used the solver and found that I have a negative time and a positive time. And, of course, it said t greater than or equal to 0. So we would want to select the time that is t equals 1.813 as our answer. So that is pretty much the presentation of the material. So what I'm going to do now is go to my TI-Nspire, and one of the functions that Fan first talked about was this rational expression where we had x plus 1 squared over x minus 3 squared, and we were looking at asymptotes with this one. So one of the things that students need to be able to do with their calculator is graph in an appropriate window. And for some students, this may seem like an appropriate window, but if you look at maybe changing our x min to negative 30 and our x max to positive 30, we might have a little better insight into those horizontal asymptotes. There's several ways to change these with the TI-Nspire. I have noticed recently that my students like to use the cursor and actually click on the x max. I mean, they can pick any of them, but we tend to start at the the x min. And so if they double click on this, then they can simply type the negative 30, and if they press tab instead of enter, it will move around to the next. It will go to the y max, and let's do a y max of about 10. Now this will not be a proportional window, but that's okay. And then it will go to your x max here, so let's put 30. And then we could go to our y min, and let's put negative 2. And then we might have a little better insight into those asymptotes, both horizontal and vertical. And one of the things that Fan suggested when she was showing you this problem is that we might want to turn the grid on, which is a fairly easy thing to do. So if I go to Menu and I go to View, and then I have an option of Grid, and I can have a dot grid or I can have a lined grid. So I've got those options. A dot grid looks like this, whereas a lined grid looks like, actually, like a little coordinate graph. And so the students might have a little better insight into those horizontal asymptotes. Fan, anything you want to add with this function that we might need to look at?
No, but I didn't know about being able to just click on those endpoints. That's really good.
Yes, it's real convenient when you have the graphing screen. Now, obviously, there is another way to do it, and that is under your menu screen. So we could have gone to Menu, and we see number 4 says Window Zoom. And for some reason, my students miss it because I think it's number 1, and their eyes focus on all the Zoom things, but it's Window Settings. And so they get this little box, and so then they can input those values here in this little template kind of thing and do the same thing. All right, so one of the things that we definitely need students to be able to do is graph a piecewise function, and on both the TI-Nspire and the TI-84, this has become quite an easy task compared to when we first were utilizing the graphing calculators in our classroom, the old-fashioned ones. So let me open a new graphing window on the Nspire. I will do that by pressing Control and the Document button. And I'm going to add graph. The nice thing about the piecewise function is there's actually a template. And so we have, beside the 9 key, there's an open book that's the catalog, but right beside it is a math template. And if I click on this, I will see lots of different templates. The one that I want is beside the log template right here. And that will give me a 2-piece piecewise. the one to the right of it will give me a multi-piece. I could do 3 or 4 or 5 pieces. So in this case, I'm going to actually type it like I see it in a textbook. So 2x minus 2, and then I like to use the tab key. So I tab, and then I want x. My inequalities are the control with the equals. You'll see them above that key here. So control equals. I want less than 3. And then again, I'm going to press the tab button, and I'll do 2x minus 4, and I'll tab again, and this time x is greater than or equal to 3. So control equal, greater than or equal to 3, and we should see that jump discontinuity. The calculator does not provide open and closed dots, but that's okay. The student should be able to understand that from the inequalities. All right. Finding zeros with the TI-Nspire is a relatively easy task. Actually, we can see that this one appears to be 1, but if we wanted to double check that, we could, or we could put in maybe a little more complicated function. So I am going to press Control Document, go to Graphs, add a third graphing page. You'll notice the tabs at the top are kind of keeping me under control here. So each one is one of those graphs that I've produced. So the graph that I'm going to do is that exponential. So we'll do our exponential key. By the way, students with the TI-Nspire have a tendency to try to use the alphabetic E as exponential, and it will not work. And they get very flustered when things won't graph like everybody else's. So caution them about that. One of the other things about the TI-Nspire is once you're in the exponent, you need to be very careful when you're finished with your exponent that you press the right arrow key so that you're back on level with the function here. Otherwise, I can stack all kind of things up in that exponent sometimes. So I want to subtract the cosine of x. Those of you who are not familiar with the Nspire, that trig key has all 6 trig functions and the 6 inverse trig functions. So minus cosine of x, and then minus 1. I think on this particular one, I can actually move that function out of the way a little bit. I think on this particular one, we wanted to look on an interval from 0 to 9, but just to save time, let's not do that right now. But let's find this 0, for instance. If this happened to represent a derivative, this would be where the derivative is changing from positive to negative and would be the location of a relative max. So we would go to Menu. There are 2 different places to find features of a graph, but Analyze Graph is probably the one that most of your students will go to because the title sort of draws them into what they need to do. Notice that number 1 is to find a 0. And so they need a lower bound, so that means I need to be to the left of the intercept, and then I need an upper bound. And I usually encourage the kids just to drag across, but there are other ways that they can actually input values. For the AP exam, we need 3 decimal place accuracy. Most of the time they'll see 2 decimal places here. So if we hover over the number and press the plus sign, we will get more digits to report on the AP exam. So it's really, really easy to find zeros here, and it's very easy to find zeros on the 84, which Fan will show you in just a few minutes. So Fan, I know we had a few other things to look at, but I want to make sure you've got time to show the TI-84.
All righty.
So I am going to stop sharing my screen because we want to make sure that people know how to use the TI-84. And okay, so now I can't drag that little thing again. Okay. There it goes. All right, Dan.
It's so nice when it works.
I know it.
All right, so we're going to go back and do some of the same problems, just showing you how to do them on the TI-84. the first one we looked at was that one, the x plus 1 squared over x minus 3 squared. I've put the equations in here first so that we can just save a little time. But the comment I do want to make here is that if you have not upgraded your operating system on your TI-84 Silver Plus Silver Edition so that you have that fraction bar, please go to the website and download the newest operating system. For the TI-84 Plus, it's 2.55, I believe, but this Alpha F1 gives you a numerator denominator, and it really helps the kids not forget parentheses so that they're not graphing the wrong thing. So let me delete that. All right, so there's the first one. Notice, remember that if it's black, the equal sign is black, that means that's turned on. That's what we'll graph, and the rest of them won't graph if the equal sign is not black. So we're going to graph it. Now, so as I tell my students, the world is not 10 by 10, so sometimes a better window helps out. If I'm doing a going towards infinity, I definitely want this to be the window to be a little bit bigger on the x's. So I'll press window up here, and I'll put in a negative 30, and go down and put 30. Now, the scale, you know, the scale represents the hash marks that are on your line, but I'm going to turn the grid on in a minute, and that scale is going to be where the grid will be also. So if you want to change your scale to 10 and have a grid only every 10, that's where we would change it. We saw that it is pretty much above the axis, so I'll go a -2 to 10 there, and then I'll graph. Now we do see it looks like it has one horizontal asymptote that we have there, so I'm going to turn that grid on. It's up here above the zoom. You see format, it's in blue, so we'll put second format, and I'll come down and turn the grid on. As Vicki said, on the TI-Nspire, we can have a dot or a line. I'm looking for asymptotes so that I want it mainly to be a line. This is the one we talked about, the horizontal asymptote is being approached from two different directions, for sure. While we're in it, we can look at the limit in a table. Second, there's table right above the graph, and we see the table, and I know that it's very close to, I'm looking for my vertical asymptote here. So I'm going to do my table set and start at that table. Well, we know that the vertical asymptote is at the 3, so I'll table set 3. And because I'm doing limits, I'm going to go up by a very small increment. So I'll look at table here. And then if we go in both directions, we've got what it's approaching. Now, if I want to change and go further out, so I want my increments not to be small because I want to go toward infinity now, I can just press the plus button and not have to go back to table set. And let's say I want to go up by 20 now. Oh, let me go back up to that 3. Well, there he is. So that now I'm going up by 20, and notice on either side it's getting closer and closer to 1 as I go both toward the positive and the negative infinity. So that was the problem that we were looking at with asymptotes. And then we were looking at derivatives at a point. So we were looking at that y equal log x and how to take the derivative at the point of log x, just for demonstration purposes here. But a lot of FRQs now, that's one of the calculator skills they have to know. So the FRQ has the students needing to be able to take a derivative at a point, a very complicated equation, meaning they really expected you to do it on the calculator. So when I graph this one, all right, I'm going to turn off that grid. Most of the time in calculus, I don't put a grid on, and I'm going to zoom standard just to get us back here. If I want to take the derivative, if you remember the problem set at 4, so I'm in the graph screen, so I'm going to go second calc, which is above the trace button, and you see derivative, that's number 6. And all you have to do is type in the number 4 and press enter, and it gives you the derivative at 4.25. Then we could go back to the home screen and do the same thing. Again, it's in one of these F2 buttons, and the F2 button is green, so you're going to go alpha F2, and you see number 3, which is in deriv. That's the old notation looking. Derivative with respect to x, or whatever letter you really want. And now I have it in y2, so I could put y2 here, but it's just more visual if I go ahead and put log of x. It's an easy one, and I come over and I want to evaluate it at 4. And so we have, there's your derivative, 0.25 again, with all those little extra numbers.
Yeah, Fan. So one of the things I think maybe would be good to put out, you may be noticing that for a long time we felt like the TI-84 and the TI-Nspire seemed so different. I think you're starting to perhaps notice that much of the notation is very similar and many of the features are the same. The TI-Nspire has a little more with the interactive ability, but as far as what the students need to be able to do on the AP exam, most of the functions look very similar and operate in a similar way. And we have somebody that's very interested in how to graph piecewise on the TI-84. So
gotcha. I'll go there.
I want to do that.
Yeah, I'll go there. But you're exactly right. With the new math print in the new operating system, they look exactly alike, most surely. All right, let's go to that piecewise function. I'll clear this one out and put it in there. All right, so on the CX, it's not on the TI-84 Plus Silver Edition. I can show you what you would need to type in for that one, but right now let's just stay on this CE or CX. It's under Math, and if you go down or up because it's closer, you've got this piecewise. This is beautiful, guys. This is really the newest thing that I just enjoy. So you've got a piecewise function. It asks you how many pieces. We knew we had 2 of them. So I'm coming on down to OK and press OK. And now look at it. Vicky's exactly right. It looks exactly like what she just had. So that I can type in the 2x minus 4. And then I'll use my arrow to cursor over to x less than 3. So you type in your x. Now your less than is a test button. Notice where test is right here on a math button, and it's blue, so you'll go second test, and it's going to be less than 3, so you're going to pull up the less than, or type the number 5 and put in your 3. Use your cursor and get it down to the next one. Left right cursor brought me over to it. I think the top one was supposed to be a 2. Okay, now going down to 2x minus 4. Cursor over and do your x greater than or equal to. Remember where it is, right here on the math button, test. So second test, greater than or equal to 3. Okay, and now let's graph. Oh, I still have that other one on. Let me get it off there so it doesn't confuse things. Beautiful. And now when you trace and you type in the number 3, it's going to only go to the button which should be a closed dot, because the other one was a less than, which is an open dot. So it's a whole lot better. However, you know, if you'll look at the screen, just notice this, where the equation is. If you have a TI-84 Plus Silver Edition, you could put in, notice at the top, in parentheses, not braces or brackets, so you put in 2x minus 2, and you're going to say times, parentheses, x less than 3. And then you're going to put where you see this comma, you're going to put a plus, and then 2x minus 4 times x greater than or equal to 3. And the Boolean algebra is what allows it to happen, because when it's false, this is a 0, so it only picks up this half, and when it's true, this is a plus, and it only picks up this half. So that would be this equation times this plus this equation times this. That was what you would do on the TI-84 Silver Edition. Luckily, the new ones have that really cool little template. So it looks like we're getting close to when we have to give it back to Michael. I want to look one time at the zeros that Vicki was talking about before down here on this equation.
Yes, I think that would be a good thing to do.
All right, good. Glad you agree.
Because zeros or intersection points are real important to some of the calculator active questions that students need to be able to do.
Right, when they tell you the 4 things the calculator has to do, one of them is to find zeros when they really mean find intersections also. So make sure they can do that. So let me graph this for you. The good thing to me about the 84 CE is that at the top it tells you you're in radian mode. So that's nice because you have to be in your trig radian mode here. So I'm going to find the zeros. These zeros were between, let's see, doesn't matter, yeah, between 0 and 9. So I'll start by finding this one right here. So your zeros are up here on the calc button. So you're going to go second calc, second on trace, and then you're going to pick 0, which is 2. Again, just like on the Nspire, you want a left bound, which would be to the left of it, the one I want, which is here, and then to the right of it, which is here. And then it says guess, but what that really means is you're supposed to be between those 2 lines. If your kids happen to move it outside of the 2 lines, it's not going to work. But if you don't move it at all, you can just enter and it will work. So there is one of your zeros. Now, and Vicki's neat little Nspire will show you all 3 of them. If you want to get them onto your home screen, if you just go back second click to your home screen and press X, there's that first 0. So now I can go back to the graph and find the second 0, and I'm just going to do that one more time. Second calc, 0, but this time I need to be to the left of the second 0. Press enter, go to the right of it, press enter, and it'll give me the last one, the second one. Go back to my home screen and press X. And the whole idea is the last point you went to on the graph is stored in the X. So if you didn't move your cursor, there's your second one. So at least I've got them on my home screen so that I don't have to write them down. So I think it's time that I have to quit sharing with you and pass it back to Michael. Anything else, Vicki, you can think of?
Well, I think maybe both of us or one of us mentioned something about possibly the 4 features or the 4 things that students need to be able to do for the AP exam on a calculator, and that is basically graph a function in an arbitrary window, and that means maybe sometimes the student themselves have to adjust the windows so that they can see the key features of the graph. They need to be able, the second is find a x-intercept, as Fan just demonstrated, or sometimes they have to find a point of intersection between 2 graphs. The third thing is they have to be able to find the derivative at a point, which we demonstrated, Fan demonstrated, and there's some screenshots in the document that you can get at the end of the webinar. And the last thing is sort of a second semester thing, and we are going to have another webinar in about a month, and we'll focus more on second semester, and that would be to approximate a definite integral using your calculator. So those are kind of the 4 main things students must be able to do for the AP exam with their technology.
And really, 2 of those are not even calculus concepts. So if we can make sure teachers are doing them before the students get to us, it would help us a lot. So graph and find points of intersection would be very, very good.
Definitely.
Sure. So just one last real quick feature here. You talked about graphing and finding the right window. A lot of students like to use Zoom Fit, and it really distorts the window. So if you knew what Zoom Fit was doing, it can really help sometimes. For example, this particular problem is only between 0 and 9. All right, so I'm just assuming maybe you couldn't find it. You graph it. All right, but I did suppose it couldn't find it, but it's only between 0 and 9. If you then do your Zoom Fit, it keeps the 0 to 9 and find all the y values between the 0 to 9. So sometimes when you cannot see the top of a function, like it crosses at 20, oh, that problem that from 10 years ago where it crossed at 20, but the kids only had a 10 by 10 screen. That really helps to find it. Then they can find their zeros better. And like one of them you did, Vicki, if you don't zoom fit, you don't really know it's just skimming off of the curve, that it actually is not crossing, definitely.
Yep.
All right, so I think Vicki and I could talk all night, but we'll give it back to Michael. All right, stop sharing. Passing the ball back to you, Michael.
Thanks so much, Fan and Vicki. As we wrap things up tonight, if you have any last-minute questions, please try to get those asked. I know Fan and Vicki will try to do their best to get those questions answered. One thing I want to share available on our website, education.ti.com. If you move under the Professional Development tab and scroll down to Webinars, two things that you might want to take note of. First is the on-demand webinars. If you haven't visited those before, say this is one of your first webinars and you're interested in learning more about calculus and some of our technology, you could select a subject area such as calculus and just peruse the calculus webinars that we've done. And what's nice is sort of in the middle of your screen here, you can see what technology it's specific for. So feel free to visit our website to learn more about those on-demand webinars. Each of those provide a link to a certificate and a link for the documents as well. Also under that webinar tab are the live webinars. So you can look at what we've posted so far for our upcoming spring series. And I think it was already mentioned, but we do have a part 2 for this webinar coming up on February 19th. So feel free to, again, register for that webinar or any other webinars that you see that you might appreciate. We're excited that the T-Cubed International Conference is coming to Baltimore this year. It's coming up in a few weeks here in Maryland, early March 8th to the 10th. It's a great place to meet people like Vicki and Fan and attend sessions and grow your professional knowledge and really meet some like-minded educators. So if you haven't done so already, we really hope that you visit our website to learn more information about the T-Cubed International Conference. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents that were used tonight. And if for some reason you don't receive these links or they're not working for you right now, just hang tight. You'll automatically get a follow-up email. And that follow-up email will contain a link to the recording, as well as a link to the certificate and a link for the documents. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. If you're in need of any additional post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or drop us an email at ti-cares@ti.com. We'd love to hear from you. Thanks so much, Vicki and Fan, for everything you shared tonight. We really appreciate it.
Thank you.
And thanks, everyone, for joining us tonight. We hope to see you back online real soon. Have a great night.
Thanks, Michael. Enjoyed it.